Hello, 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 hello. Okay. Uh, okay, I think the microphone work well. Okay. Then, uh, okay, today we talk about the digital logic circuit. Okay, and so far we have talked about many circuits, right? For example, we DC transient circuit, and then also AC circuit, right? AC circuit. We also talk about three-phase circuit, right? Three-phase circuit, and about for AC three-phase, mostly we use it in uh, power system, right? Power circuit, and then junction circuit, uh, three-phase circuit, and maybe uh, electronic circuit, some electronic circuit. But we mainly focus on the diode, right? Diode circuit, and some on transistor, right? Circuit, transistor circuit. Then today we talk about the digital logic, okay, circuit, and yeah, I think it won't take long time, maybe just 1 hour. And so we have two types of circuit nowadays that we call analog signal. So mostly what we talked previously in the previous lecture, we the signal is in analog form, right? Analog means is continuous signal, right? Continuous like electric signal, and or any signal that we can uh, measure in continuously, like voltage, temperature, force, or any variable. Mostly is in analog signal in our real life, but uh, people develop the some logic signal is includes only 0 and 1. It means on and off signal. 0 may be off and 1 is on signal. We call a digital signal. Right? So a kind of digital signal may be a discontinuous or discrete signal. Is the finite number, right? So sometimes if we count 0, 1, 2, 3, because this is a digit number, right? Digit number. Or if we use some real number or continuous number, it means from 0 to 1, if you have 0 0.01, 0 0.02, or 1.1, 1.25. So any number continuously, but in digital signal is discontinuous, right? And mostly in digital logic, we use only the signal of 0 and 1. The signal is there and it's not there. And we can make a combination of 0 and 1 to represent the uh, some continuous signal in step form, right? For example, we measure temperature in step 1, 2, 3, 4, 5, like this. And this is the sensor output, right? So in fact, it may be the continuous signal, but once we receive the signal and send the signal, sometimes we use in digital form. Okay, so this is an example. If we have the analog clock, right? It's so we have the hour and minute pin, right? To pointer to the clock to inform our time, right? And we will have in digital form as well today, right? This is digital clock or the voltmeter. The voltmeter in analog form, right? And nowadays we have the digital voltmeter or ammeter, right? It's shown in digital log digit form, right? Or the joystick, we may have analog joystick or digital control, right? And even in the air conditioning system, right? Previously we use analog control, right? Like resistor, right? Variable resistor. And nowadays we can have in digital form, right? And for if you use the remote control to your air conditioning, so you cannot, for example, you can control the air condition for 19 degrees Celsius and maybe 19.5 degrees Celsius. You can set it to 20 degrees Celsius and 20.5 degrees Celsius, and you cannot try to control the temperature to 19.2, for example. It's not allowed, right, in digital control system, but for analog system, it may be possible. But the analog system may be not so accurate, right, with the accuracy with the device may be not very accurate. So the digital event is not into the detail in between the digit, but it's more accurate, right? It's stepwise, but maybe sometimes it's more accurate, right? For this type of control system, for nowadays, people mostly use digital system in the real life or in the industrial control system or even in your daily life living, right? You're familiar with digital signal. And digital signal can represent the analog signal, right? This can be represent the analog device with the more accurate, right? More precise uh, sensing, for example. Okay. Even is stepwise, but it can be more accurate, right? For example, this voltmeter is continuous signal, but the device may not be very accurate comparing to digital sensor device. And for the digital signal is if we use the binary signal. Binary means only 0 and 1. It's binary signal. So it's a signal carrying only two discrete values. It can be only 0 or 1. 1 is may not be 1 volt. It could be maybe 5 volt or maybe 3 volt. If the signal is there, right, and 0 volt and 5 volt, and we can, for example, if we have the power source 5 volt and we have switch to some voltage, right? This is maybe voltage voltmeter. So if we switch on, the signal is there. If switch on, the signal would be 5, right? And if off, it will be 0. So if we switch on and off, we can get a kind of signal. This is on and off, and we can send some code, right? We can send some code to to your friend, right? Without talking, right? Okay, here. So we can generate some information with only 0 and 1, right? And we use it also in computer and in many controller, in the PLC control, in the microcontroller, or in your smartphone. Behind is this digital signal, but it's a lot of signal. It's two power something signal, so it can generate a large code. Okay. So if we talk about the binary number system, so it would be in the form of base 2, right? The number with base 2. So we familiar with a decimal system with base 10, right? Base 10. So in base 10, if we say 372 is maybe 300, right? 300. And then 70 and 2, right? 2. So the last digit is 10 power 0 and 10 power 1 and 10 power 2 like this, right? And for the binary system is in this similar computation, but it's in the base 2 system, right? Base 2 system. So if we have 10110 like this, it means the last digits will be multiplied with 2 power 0, and then with 2 power 1, with 2 power 2, 2 power 3, and so on. So in this case, the value is 0 into 2 power 0. This means 0. 1 to 2 means 2, and this is 4, right? This is 2, this is 0, this is 2, this is 4, and this is 0, and this is 16, right? So in this case, the total value is 22, right? 22 of base 10. So 10110 is in base 2 is equal to 22 of base 10. So with this combination, we can represent any value with only 0 and 1, right? Only only with the binary number, right? 2 digits, only on and off signal. So we can represent the number with the axis of the voltage, right? The voltage on and off, on and off. So with this, we can represent the mathematical value into the electronic signal, right? With on-off signal using binary number system, right? So, for example, if we have the decimal number from 0 to 16, right? We can represent 0 with the binary number. 0 is 0, right? 1 is 1. 2 would be 1, 0, because this 0 is into 2 power 0, and this is into 2 power 1, right? It will represent the number of 2. And then 2 and 1 would be 3, right? And then 4, this is 2 power 2, 4. 5, 6, 7, 8, 9, 10, until 16, right? We get this value, right? And this is the value is for 111. If we use 4 digits, the maximum value is 15, right? From 0 to 15, right? We can represent 16 number, right? 16 number from 0 to 15 here with 4 digits of binary here. And I leave this slide for you to check your understanding, right? Yeah. For the digit value, right? For example, 3.25, we also have this value. 3 is 10 power 0. 2 would be 10 power minus 1, and 5 would be into 10 power minus 2 in this case. So for binary system is also similar, but with the base of 2, right? 1 will be into, sorry. 1 will be in, 0 will be into 2 power 0, and this is 2 power 1, right? And this is will be 2 power minus 1, minus 2, minus 3, like this. So this value will represent 2.375 in base 10, right? Okay. So this is just for you to practice your understanding. I think it's not so difficult. And we can add and subtract the binary system, similar to the decimal system, right? 5 plus 6 is 11 for binary. In the addition rule, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 and is 0 with a carry of 1, right? So if we have 1, for example, 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 0 with a carry of 1. Right? This value. And so on. And for the subtraction rules, 0 minus 0 is 1. 1 minus 0 will be 1. 1 minus 1 is 0. And 0 minus 1 is we will get 1 with a borrow of 1. 0 minus 1 is 1 with a borrow of 1. For example, 9 minus 5, we get 4, right? 1 minus 1 is 0. 0 minus 0 is 0. 0 minus 1 is would be 1 with a borrow of 1, right? This one. This borrow we get 0, 1, 0, like this. Okay, and for the multiplication and division rule, the rule of multiplication, 0 into 0 is 0. 0 into 1 is 0. 0 into n is 0. 1 to 1, only 1 to 1 we get 1. And for division rule, we can divide by only by 1, right? We cannot divide the number by 0. 0 divided by 1 is 0. 1 by 1 is 1. This is just simple rule. Okay, and we can form the hexadecimal system by the binary number, right? And with 4 digits, right? This is what we call 4-bit, right? 0 is all 0 and 1, 2, 3 into 4 for the base 16, right? We call base 16. Hexadecimal system is the base of is the base of 16, right? This is 1 until 0 to 9, 10, 11, 12, 13, 14, and then 15, right? And with 0, we have totally is 16 value here. Okay. With 4 digits like this, right? Okay. And we can form the binary code decimal, or we call BCD code. The BCD is binary code decimal from 0 to 9 with 4 digits, right? This will be represent 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then from the value from 0 to 9 can be represented by the by digital logic, right? In this case, for example, we may have the lamp, right? 4 lamp with 4 switch, right? This is maybe supplied by some battery, right? By battery. This is positive pole and negative pole. So if switch on one switch on, we get 1, right? 1. If this switch is off, we get this switch on, we get 2, right? If I switch on through this switch, these 2 lamp on is mean the number of 10, right? So we can represent number 0 to 9 by 4 switch, right? If if this switch on and this switch on is mean the value of 9, for example. This is called binary code decimal. Okay, and we also have gray code. The gray code is also 1, 2, sorry, 0, 1, 2, 3, 4, 5, 6, 7. It's 8 value. It's 8 number, right? It's 8 number. With this code that with the gray code, the binary change only one position, right? Here, but 0 to 1. And then we change here 0 to 1. And then we change 1 to 0 here. And then from this, we change 0 to 1 here. And then change 0 to 1 here. And then 1 to 0. And then 1 to 0 here. So change only one position. Change only one position. And then one position, which can be used for counting. Right? Count up and count down. Okay. So now we will talk about the Boolean algebra. The Boolean algebra is the logic, or we can call it, we represent true and false logic. Right? The signal is there, and the signal is not there, it's false. Right? We thought, for example, 5 volt is there, and 0 volt will be false. And the 1 will be represent positive logic, and 0 is the negative logic. We call logic function, and we can carry out this type of logical function or Boolean by the tool called truth table. So we can form truth table to solve this type of logic. Okay. There is also another type to solve this logic using Boolean, and sometimes we call Canonical map, and we can solve it by some derivative. And but I think maybe we not go to too much detail. That we learn if we learn about digital signal processing or digital control system, so that maybe take another course. Right? Okay. So the truth table will list all the possible value. Okay, all of the possible values. Okay. So for example, I introduce the logic called AND and OR gate. Right? If we pass two logic to OR gate, it will be under the logic of OR. For example, the rule of OR is a kind of addition rule. Addition rule is 0 or 0. 0 or 0 is means 0. 0 or 1 would be 1. 1 or 0 is 1. 1 or 1 is 1. Right? 1 or 1, 1. Okay. That like this. Okay. For example, if I say maybe orange, right? Orange open. Orange open. If the orange open, so if the object is orange is 2, the object is pen is also 2, right? It means any is also 2, right? This is all logic. Or if we form in truth table, if x is 0, y is 0, the output c is 0. If x 0 or 1, the answer is 1. 1 or 0, the answer is 1. 1 or 1, the answer is 1, right? This is the all circuit, right? If I switch on switch A, I close switch A, the lamp will turn on. Either I close switch B, the lamp also turn on, right? So A or B can turn on the lamp. So if turn on both A and B, the lamp will turn on also. So in this case, which one is on? The output would be on, like this. Okay. On the other hand, for the logical AND, the AND will be represented by the multiplication rule: 0 into 0, 0, 0 into 1, 0, 0 into 1 into 0 is 0, 1 into 1 would be 1 here, right? So the AND will be, we use this symbol for AND gate. Right? X is the signal count and Y is the signal count. C is the output. If X is 0, Y is 0, C will be 0. If X is 0, Y is 1, the output is 1 here. Then we can also represent by the switch here. A and B, both A and B must close, right? Must close. The lamp will be on, right? If either A 1, B 0, the lamp will be turned off, right? We also have another type of representation like this. Sorry, like this. This is output. Oh. This is output. I'm sorry. Output. Right. Another type of like this, and this is maybe A and B contact. This is the output contact. If A come, the output come out. B come, the output also come out. In this case, the diagram would be here, right? This is O, and this is N. This is A and B. Then the output will come, right? Like this. The contact open. This is open, and this is the close contact. Contact. We call this type of diagram as a ladder diagram. Then if you learn about PLC, programmable logic control, you will draw the code in ladder diagram. Okay. Here, just introduce you that I won't talk about this diagram. Okay. Okay, we also have NOT gate. NOT is mean we inverse. If X is 1, not X is 0, right? X, the output C. C equal to X bar, or the inverse of X is not X, right? If X is 0, the output would be 1. So this type of gate inverse the input to the opposite value. Okay, not. Okay, for example, we if the switch is normally closed like this, all right? This is A. If A comes, it will be inverse, right? It's been the signal is on. If we change the A value, it's become open, right? The signal will be off, for example. Okay, so you can use a combination of many gates together, right? For example, if X and Y are together, and then we inverse the output. So this is X plus Y, and this is X plus Y, then we inverse, right? Inverse, or not gate, or we can call NOR gate, right? Or then not, right? And we can also have and then not gate, right? This is X and Y, and the output will be X and Y and inverse, right? So C here. Okay. So if we form the truth table, X and Y is 0 and Y is 0. If X 0, Y 0, X and X or Y, sorry, X plus Y, X or Y will be 0. If X 0, Y 0, X or Y is 1. If X is 1, Y is 0. the output is 1. 1 or 1 would be 1. Then here, just like this. If I draw x plus y inverse, not x plus y not. If x plus y is 0, its inverse would be 1, right? Not, its inverse would be 1. If it's 1, the output would be 0. If it's 1, the output would be 0. If it's 1, the output would be 0, right? So for x or y, inverse is 1, 0, 0, 0, right? X or y, 1, 0, 0, 0. And if we use this circuit, x and then not x and x bar, y and not y, y bar, and add together is mean x inverse into y inverse, what we get from here. So I draw one table. I draw one table here. Maybe here. X and y. 0, 0, 0, 1, 1, 0, 1, 1. And I want to get x bar. And then y bar. And x bar into y bar. Okay. Now let's see what is x bar. If x is 0, the inverse is 1. If x is 0, the inverse is 1. If x is 1, the inverse is 0. If x is 1, the inverse is 0. And for y, if y is 0, the inverse is 1. Y is 1, inverse is 0. Y is 0, inverse is 1. Y is 1, its inverse is 0. And when we add it together, 1 and 1 will be 1, but 1 and 0, we get 0, right? 0 and 1 is 0. 0, 0 will be 0. So here we get the same solution, right? Same solution. So in this case, just to prove x plus y inverse equal to x inverse and y inverse. Okay, here, just to show this rule, right? So let's see another rule. If we add x and y together and then we inverse, what happens? Yeah. So I will draw the table here. Right? So if we form the two tables, x and y, so x will be 0, 0, 0, 1, 1, 0, 1, 1. Then x into y, right? We would like x into y. X into y, 0 and 0 is 0. 0 and 1, we get 0. 1 into 0 is 0. 1 and 1, we just get 1. And then we inverse the signal. X and y inverse. 0 inverse is 1. 0 inverse to 1. 0 inverse to 1. 1 inverse to 0, we get this output, right? So therefore, if x is 0, y 0, the output is 1. Just like this, okay? So if we use another type of logic circuit, x then not x, here x bar, y and not y, and we all together, the output will be x bar plus y bar, like this. And x bar plus y bar, what is the value? So I prove here, right? X bar, y bar, maybe x, y, x bar, y bar and x bar plus y bar 0, 0, 1, 1, 0, 1, 0, 1. X bar 0, so x bar is 1, right? Here x bar is 1, x bar is 0, x bar is 0. Y bar, y is 0, y bar would be 1. 1, we get 0. Y0, we get 1. Y1, we get 0. So we add this signal together, right? It's all okay, right? Become all. 1 or 1 is 1. 1 or 0 is 1. 0 or 1 is 1. 0 or 0 is 0. See that we can also get this answer the same with this answer, right? So this circuit is equivalent to this circuit. So just to prove that x and y inverse equal to x inverse plus y inverse here, right? Therefore, in this slide, we just prove x plus y inverse equal to x inverse multiply y inverse, right? X or y, x or y inverse, right? X or y and inverse is x inverse and y inverse. And another rule is x and y, then inverse equal to x inverse or y inverse. Okay, and then we call De Morgan theorem. Okay. So an equation. So we have so many rules here. Okay, like the 0 or x is equal to x anyway, right? 0 or x, so if we have OR gate, and 1 is exactly 0, and if x is come, what is the output? So if x here, if x is 0, if x is 0, the output will be C, right? The output, if x is 0, the output will be 0. X or 0, 0 or 0 is 0. If x is 1, the output, if x is 1, the output is 1. So in this case, 0 with x or x will always x, right? For example. And 1 or x will be always 1, right? Like this. If we have 1 pin, is exactly 1 all the time. Oh, okay. Say 1 all the time. I cannot write in this area, I don't know. And if x is 0, what happens? If x is 0, the output, if x is 0 or 1, we get 1. If x is 1, that's always 1. The output always 1, just like this. So this is just true. Okay. And you can prove some rule by truth table. For example, which rule x plus, for example, which x plus y into x to x. For example, the rule number 16. The rule number 16 can be proved with this truth table, right? So if we have x and y 0, 0, 0, 1, 1, 0, 1, 1, x or y will be 0. 0 or 1 would be 1, right? 1 or 0, we get 1. 1 or 1, we get 1, right? And if we put add x into here, 0 and 0, we get 0. 0 and 1, we get 0. 1 and 1, we get 1. 1 and 1, we get 1. See, the output is equal to x, right? Therefore, x and x or y, right? X and x or y will equal to x. So this is just true, okay? If we draw the logic circuit, for example, with this circuit. How to draw the circuit? We have X and X or Y, right? I can draw like this. So if this is X, this is Y, X or Y, right? This is the output, this is X or Y, and we AND with, this is OR gate, right? And this is AND gate. This X or Y AND with X. So X come here again, right? This is a kind of circuit. Okay. So I would like you to try something. For example, if we have X, Y, Z, how to draw this? How to draw X and Y plus C. If we have X, we have signal Y, we have input C. How to draw X and Y or C? So first, Y or C first, right? This is Y or C, and this come to AND with X signal, right? This is O and this is AND, right? And we get the output. Okay, maybe W, yeah. X, Y, Z, W. So if I would like you to solve, so if X is 0, Y is 1, C is 0, what is W? Can you solve this? So in this case, you can see that you can solve from the algebra here. If Y is 1, X is 0, right? Into Y, if Y is 1, C is 0. Is 1 or 0. This output is 1, right? It's 0 into 1 is will be 0, right? So from the circuit, if Y is 1, C is 0, and X is 0, what is the output? If Y is 1, C is 0. The signal out here is 1, right? And 1 and 0 AND together, we will get 0 output, right? So you can solve with the formula, or you can solve with this circuit as well. Or you can form this truth table to see what happened, right? Okay. So to form the truth table with more than 2 input, we just add some more column and more row into the truth table. Okay, I will show you some example. For example, if we would like to draw the truth table of this logic X and Y plus X and C. So how to get the truth table? So we will have 3 input value, right? It will be X, Y, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, right? 1, 0, 0, 1, 0, 1, 1, 1, 1. Just like this, just to get all possible combination, right? Here. All possible combination. Right? Do I miss something? Oh no, I missed 0. And then 1, 1, 1. Like this. Okay, let me read over. Which one? Here, right? X, Y, C. Okay, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1. Oh, 100 first, right? 100, 101, 110, 111, right? We get this combination, 8 combination, and then we solve for x and y, like x and y, and what is x and z, right? And then what is x and y or x and z here? X and 1, so we can get x and 1 is 0, x and 1 is 0, x and 1 0, x and y also 0. This is 0, this is 0, and this is just 1 and 1, just like this. And x and z, right? X and z is 0, 0, 0, 0, 0. In x and z, we get 1 here, we get 0 here and 1 here. We add it together, it's 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, 1, right? 0, 0, 0, 0, 0, 1, 1, 1. Okay, here is the output, right? So I suggest you to try practice on this type of how to make the truth table, right? And okay, and how to draw the logic. If I give you the some Boolean algebra to construct the uh, truth table or to construct the logic gate in this form, right? In this form here. Okay. Uh, if we have Boolean algebra, if we have Boolean algebra and we construct logic circuit and we can construct the truth table here. Okay. This is the I just would like you to be able to do this, or if you have logic circuit, you get the algebra as well. Okay. So we also have some two type of important logic is we call the sum of product and the product of sum. And this is the sum of product circuit, right? And we have two signal to add together. Here we get x into y, right? This we call the product. W and Z, W and Z, this is the product, and we all together we call the sum of product. It's all and then all later is the sum of product. And if we pass the signal to all logic gate, A or B is A sum B, right? C or D is C sum D here, and we add together. And here we call the product of sum. So we have sum of product of sum. Okay. Okay, this is just some example to use this rule, right? The algebra rule. So we have so many rules, right? So you don't need to remember all. You can bring A4 sheet, right? It's this rule. Okay. So we can derive the complex function into simple function using the rule, right? So I will go a bit fast with this. Okay, so in this case we have A inverse and B inverse and D plus A bar and B and D plus B and C and D. So we can analyze this complex signal, right, using the algebra rule, just like the mathematical rule. Okay, similar to mathematical rule. So the function is this. If we use rule number 14, right, here we have B inverse and B, and the common is A inverse and D. So we move A inverse and D from the bracket like this. So these two terms can be represented with this term, right? With the rule 14 here. The rule 14 states that if x is outside the bracket, we can multiply it to y and c, right? So it's just similar to mathematical rule here. So we move a bar and b here, and the last two terms remain the same like this. Then we can use rule 4, right? Rule 4, what is rule number 4? Rule number 4 is if x or its inverse is always 1, right? If we have x here, and if we inverse x, right, inverse x, we always get x. So if x is 1, for example, if x is 1, 1 is here, is the output is always 1. If x is 0, the 0, but inverse is would be 1, the output is 1 again. Okay, it's always 1 here, right? So in this case, this output is always 1. Okay, so one and any signal is will be that signal. So we get here like this, and after that you can just follow many rule, and then finally we get this output here: a bar plus c and then d. So this is equal to a inverse plus c into d. So it's become more simple, right? So we can solve with this rule as well. Okay. Okay. I suggest you to practice this slide. Okay. For example, if we have this algebra, and the command is to construct the truth table, to prepare the truth table. So I will give some examples. So for maybe equation A, right? We have x, y, c, x, y, c, x bar. Okay. What is the truth table look like? X, x, y, c. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So maybe this one first, right? X and Y, X, X, or Y, or C, but we inverse it. What is this value? X or Y or C. This would be 0, right? But it's inverse, so it's become 1. Okay. O 1, the output would be 1, right? 0 or 1, the output is 1. But inverse, the inverse is becomes 0. 0 or 1 is 1. The inverse becomes 0. 0 or 1, inverse becomes 0. 1 or 0 is 1, and the inverse is 0. 1, the inverse is 0. 1, 0, inverse is 0. 1, inverse is 0. Like this. And the next, maybe x and y and c first. X and y and c. X and y and c. 0 and 0 and 0. This would be 0. 0 and 0 is 0. 0 and 1 is and 0. 0 and anything is 0. Is 1, 0, 0. If the 0 is there, it's 0. If 0 is there, it's 0, right? All 1, we get 1, right? And we add this into, we add this value into inverse of x, right? We add this value into the inverse of x. So this is x, y, c. Then we add it with the inverse of x. What happened? 0, 0 and the inverse of x, right? 0 and 1, we get 0. In fact, 0 and anything, we get 0, right? If the 0 is there, it's and with 0 and with it 1 is 0. It's 0. It's 0. So 1 and the inverse of x. In this case, the inverse of x is 0, right? Because x is 1. So here we also get 0. So finally, the output is, this is A and this is B, right? This is A and this is B. A plus B, right? The output is A plus B. The final output is this term or this term, 1 or 0. We get 1. 0, 0, 0, 0, 0, 0. The remaining is all 0. Right? And this is solution of equation number A, right? Here. So we get 1 and all 0. Okay. So I just suggest you to practice with equation B and equation C by yourself, and this is the solution is here. Okay. Just do it first. Then you check your solution with the solution in this page. Okay. Right? Any question so far? Okay, not too difficult, right? But there is some process and some practice you need to do, I think. Okay. Then we also have some two other type of gate. We call NAND and NOR gate, and then not, and then inverses. We call NAND gate. And NOR gate is OR and then not. It's NOR gate here. We can use this symbol. This is symbol NAND gate, and this is NOR gate. It's equal to and then not. Inverse the output, right? A and B, and we inverse the output, right? And we also know that A and B inverse is equal to A inverse plus B inverse, right? With this theory. With which one? Here. With De Morgan theorem, you know. Here. Okay. So what is the output of NAND logic? If we have the signal A and B, we construct this truth table. A, B, A, B, A, B, here, right? A and B, A and B, A and B is 0, but we inverse, we get 1. A, 0 and 1. A and B is 0, we inverse, we get 1, right? A and B is 0, inverse, we get 1. A and B is 1, the inverse is 0. Yeah. And if we solve for A bar plus B bar, A is 0, inverse is 1. A is 0, inverse is 1. 1, 0, 1, 0. B is 0, inverse is 1. B is 1, the inverse is 0. 0, 1, 0, 1, like this, right? So in this case, A, B, all together, if we use A bar or B bar, 1 or 1, we get 1. 1 or 0, we get 1. 0 or 1, we also get 1. 0 or 0, we also get 0. So this is equal, right? A and B inverse equal to A inverse or 2 into B inverse, like this. And similar for NOR gate, right? NOR gate in this case. Yeah. A or B, we get 0, but it inverse, right? A or B, we get 0. Inverse will be 1, like this. Okay. 0 or 1, we get 1. The inverse is 0. 1 or 0, we get 1, but the inverse, there, 0. 1 or 1, we get 1, right? And the inverse is 0, just like this. Okay. So try to solve this table for the remaining for yourself. For example, A bar into B bar, we get the same value. Okay. And also we can have the logic called exclusive OR. What is the exclusive OR logic? Yeah. Exclusive OR is this logic, but the output of this logic, you get this truth table. If x 0, y 0, c is 0. If x 0, y is 1, c is 1. If x is 1, 0, this is 1. It's 1 and 1, we get 0. It means that if x and y different, if x and y is different, if x not equal to y, if x not equal to y, the output is 1. If x is equal to y, the output of is 0. So in this case, if equal, the output is 0. It's not equal, the output is 1. Okay, it's 1 and 1 with 0, we get 1. And if it's equal 1 and 1, we get 0. So this is spatial gate, right? We call exclusive OR gate. Exclusive OR gate, we use this symbol X, the symbol OR with the circle, right? Here. Exclusive OR, okay. And this is the output. Okay. It's equal to the, if we represent exclusive OR with the simple gate, this will be X, Y all together, and with the NAND gate, and then it AND together again with C. So in this case, if X is 0, Y 0, we get C is 0. X 1, Y 1, we get C 1. Like this. If both are 1, we get the output as 0. Okay, you can prove this. Okay, maybe this would be good if you try to check it out. Okay. Okay, I think I come to the end of the slide already. This is just an example when we apply this logic to some control system. This is the simple boiling system, right? To start the boiler, to heating something. So the boiler we have the chimney, right? So when you boil something, and we have the chimney, right? Put the smoke out there, right? So we turn on the boiler by get some valve with the fuel. Right? We feed the fuel, but they usually turn on if the chimney is not blocked, right? Here, B will be the chimney is blocked or not blocked. If the chimney is not blocked, so it's not gate is there. And right, if the chimney is not blocked, right? You can see here, it's not blocked. The house is cold, so it's cold on us. The house is cold here. The house is cold. C signal maybe from some temperature sensor, right? The house is cold. So this is cold, right? Maybe temp sensor in degrees Celsius, right? and the pilot light is lit right here, and the pilot light is lit. Then open the main fuel valve, right? V here is a fuel valve. This is V here, right? We turn on. So this is maybe C is also. So if the chimney is not blocked, so it's inverse, right? This is V inverse. It's not, and it is cold, and the pilot light is lit. Then we turn on, right? The boolean is there, right? It's all and together, right? And together because this is and right? And together we get the output here. Okay, this is an example. But also this is an example for the pumping example, right? So if in this case this is the pump system, the pump will pump the water for the lower tanks, right? From the lower tank to the upper tank. If the water fill up into the level L3, the pump will be stopped here. Okay. So if the water in this level, if this sensor send a signal, the pump will be stopped like this. So if level equal to 1 here, if L1 is 1, it means the water is above L1, we can pump, right? But if the water is this level, if not, right? If L1 is not activated, right? It means if the water above L1, L1 is 1. If the water below L1, L1 is 0. So only the pump can operate when the water L1 is on, right? It means this L1 is on. And L2, if L2 is 0, if L2 is 0, it means if the water below L2, then the pump is on, right? The pump would be on. Until if the pump is on until if the water reach L3, if L3 on, become 1, the pump will be stopped, right? Until L3 equal 1, the tank is full, right? Or L1 is 0. If L1 is 0, the pump also off, right? Here this is the logic. So in this case, the pump will operate until the level reach L3. It will be turned off, right? But when we use the water, okay, if we use the water until the water below L2, the pump start pumping again, right? In this case, like this. Okay, this is what we want. It's just like this. So in this case, we if L1 is 1 and L2 is 0, then we can construct this type of circuit, right? L1 is 1, L2 is not L2 here, right? And we AND it together. And the output come here, and L3 must be 1. And if L3 is 1, it will stop. So if L3 is 1, it will stop. It's not here, not L3 here, right? And we feed the signal back to all here. This pump is on until this signal. Okay, this is just to show you some example, right, on the application. Okay, then this will be your last homework here. So for example, to determine the Boolean function, right? What is it? This is A and B and inverse, right? And this is B, C and D, then inverse. This is E inverse. All and together. So F would be A into B inverse, C into D inverse, and then into E inverse, for example. This is not difficult, right? Here, okay. And this is also to construct the equation. So any truth table for your practice? No? Just this, but this to draw the circuit. to draw this circuit, right? If you have this, to draw this type of circuit, to draw this type of circuit, right? Okay. Okay, and this is to determine some truth table. Okay, this is truth table for this. Okay. This is nothing, just A here, and this is not A, and together. If A is 1, if A is 1, the output is 0. If A is 0, the output is 1. This is A, just A bar. And this is after you get the output. After you get any output, the F will be the output inverse, right? Okay, just like that. Okay, I leave this homework for you, and I already set the deadline of this homework, right? So, okay, I think I will stop here. Okay. Any question?